The next one is a still synchronous parallel model. In SSP model, the fastest worker can outpace the C steps than the slowest worker. The C is the stillness. In SSP model, it still has some ad hoc and bounded stillness. We already have 3 parallel models. Do these suffice in practice? The second problem is hard to write parallel programs. For example, MapReduce, it lacks of support for iterative graph computations. The vertex-centric models like Praggle, GraphLab, they ask users to think like a vertex. The block-centric model inherits vertex programming. We can bear with this, but the users have to recast existing graph algorithms into a new model. On the one hand, it is non-trivial for users to learn how to program in new parallel models. And on the other hand, a number of the sequential graph algorithms are already in place after decades of study. Other problems include consistency, no guarantees on termination. All of these made parallel graph computation is a privilege of experienced users. The total cost of ownership is beyond the reach of small businesses. To solve these problems, we proposed a new parallel model, Adaptive Asynchronous Parallel Model, or AAP. The properties of AAP include model switch, programming simplicity, expressive power, convergence guarantees, graph-level optimization, and good performance. I will introduce them in details in the next slides. So AAP is a more flexible parallel computation model. It inherits the benefits of BSP and AP and reduces stragglers and still computations. First, let's see how AAP did better. Intuitively, in AAP, each worker maintains parameters and dynamically adjusts its progress relative to other workers and the stillness of its accumulated changes. Continue the example we mentioned above. In AAP, this is the timing of AAP. We can find AAP ask P3 waits for 1 time unit and it starts at time 8. So it can converge in less runs by utilizing the latest updates from the faster workers. In AAP, slow workers may wait longer to reduce the still computations. This is not an artificial scenario. The stragglers are very common in real-life graph computations. We case studied a run of PageRank among 32 workers. This is the timing diagram of a BSP model. The x-axis is the time, and the y-axis, in y-axis there are 32 workers. One can easily find that P12 is a straggler, and it dominates the running time, while the other 31 workers mostly idled. So in AAP, when have the straggler will slow down the whole process. AP did slightly better. The idling was substantially reduced. However, the faster workers performed far more redundant runs, so it suffers from redundant computation and communication. This is SSP, where the stillness equals set to 5. It did better at the beginning, but it degraded to BSP later. So sometimes SSP also suffers from the straggler. Now let's see the AAP. In AAP, each worker dynamically adjusts its pace based on the stillness and the relative progress. From the figure, we can observe that until round 6, the messages arrive in a near uniform speed. At round 6, the P12 is a straggler, adjusts to wait messages from 31 workers based on predicted running time and message arrive rate. And starting from the round 3, the faster workers are grouped together and run BSP within the group. Meanwhile, this group and the straggler are under AP. So we can find in AAP, it adaptively switching among these models at different stages of a single execution. Hence, it reduces both stragglers and redundant still computation. In AAP, each worker adaptively adjusts the relative progress after each round, so it can optimize the process like this, reduce the idle time. Better still, AAP subsumes BSP, AP, and SSP. For BSP, it suspends worker I if the round number of worker I is greater than the minimum round number. For AP, it just says each worker processes at once when receiving message. For SSP, it said suspend worker I if the round number is greater than the minimum round number plus a constant C. So AAP can perform almost optimal. We developed a system called Grape Plus, implementing AAP model. To handle the second problem about hard-to programming at adopting a programming model of Grape. Grape is our previous work published on Sigmod 2017. For class query Q, the input is a graph G and the query Q. The output is the answers to Q in G. We ask users to provide three existing sequential functions. The first is p-eval, is a sequential algorithm for Q for partial evaluation. Second is inc-eval, a sequential incremental algorithm for Q. The third is Jingbo, which takes a union of partial results. So it is much easier for people who are more familiar with conventional programming. Grape Plus employed data partitioned parallelism or shared nothing architecture. A graph G is partitioned to fragments G1 to Gn and distributed to workers. Upon receiving a query Q, it answers in three phases. First, each worker may trigger p-eval to evaluate QGI in parallel. Then it repeats incremental inc-eval by trading messages MI between different workers as updates. And finally, it assembles partial results when it reaches a fixed point. The parallel processing in Grape Plus is a principled approach based on partial and incremental evaluation. This is the workflow of the Grape Plus. When receiving a query Q, the workers may trigger p-eval, and then it repeats inc-eval. With the AAP, the worker can adjust its relative progress. And finally, the master will trigger the assemble to assemble the partial results to a final result. It is remarkable that here, p-eval, inc-eval, and assemble are existing sequential algorithms. Next, let's see the expressive power of AAP. We say a parallel model M1 optimally simulates model M2 if there exists a compilation algorithm that transforms any program with cost C on M2 to a program with cost OC on M1. We proposed and proved a simulation theorem. MapReduce, BSP, AP, SSP, and PRAM models are optimally simulated by AAP. We remarked that AAP is not limited to graph computations, and existing parallel algorithms are readily migrated to Grape Plus. With the simulation theorem, Grape Plus is as powerful as the existing graph systems. We also proved the convergence guarantee. We identified three conditions. T1, update parameters take values from a finite domain. T2 is inc-eval is contracting. T3, inc-eval is monotonic. When the first two conditions are satisfied, the program is guaranteed to terminate. When all three conditions are satisfied, the program has a Church-Russell property. Thus, all asynchronous runs converge at the same correct result. To the best of our knowledge, this is the first condition for Church-Russell property. Grape Plus also has a feature of graph-level optimization. P-eval and inc-eval inherit all optimization technologies developed for sequential algorithms and graphs. For example, indexing, compression. They are hard for vertex-centric or block-centric systems. Graph Plus has this unique feature because it applies a single machine algorithms to graph fragments. Next, let's see the performance of Graph Plus. It outperforms BSP, AP, and SSP, and it outperforms the state-of-art systems. The table shows PageRank and SSP compared with the Giraffe, GraphLab, and PowerSwitch. We also conducted a proof of concept in an online payment company on fraud detection. These are some additional evaluations on scale-up of Graph Plus, the impact of partitioning, the speed up in larger scale settings. Graph Plus has this performance gain because it reduces the redundant computations. To summarize, we proposed a new system called Graph Plus with the AAP model. It has a principled approach based on partial evaluation and incremental evaluation. It has a new parallel model, we call it AAP. It remedies the limitation of BSP and AP. It's easy of programming. It has a high expressive power, can optimally simulate BSP, AP, SSP, MapReduce, and PRAN. It has convergence guarantees, and it inherits all graph level optimizations and have good performance. The future work include improve adjustment function for different computations. And another future work is handle steering updates. We think AAP is promising for larger scale graph computations. Thank you.
All right, time for a few questions. Use mic.
So thanks for the talk. So I have two questions. So how does the other important graph analytics algorithms, such as pattern matching or subgraph isomorphism, can benefit from your supposed processing model?
Repeat the question.
Yeah, good question. Actually, we have implemented the pattern matching, like subgraph isomorphism in our system graph. It can just, because the subgraph isomorphism has a locality, so in the p-eval, we prefetch the r-round of the diameter of the pattern, and then in eq-eval, we just trigger the existing sequential subgraph isomorphism algorithm, like VF2 or tube ISO. It can just run and can get the correct results.
I see. So can I have one more question?
Go for it, yeah.
Yeah. So the next question is that, so you pointed out that it is hard to program and debug the asynchronous programming model, processing model. So how will the proposed model handle that issue?
Sorry?
So you pointed out that it is hard to program and debug the asynchronous program.
Yeah.
And why is that, and how does your model can solve this problem?
Yeah, we think the vertex-centric model asks users to casting the existing algorithms into that new model, and ask users to think like a vertex. But we just parallelizing existing sequential algorithms. Users just don't need to care about the distributed setting and write the sequential algorithm. We can handle that to a distributed setting. So we think it's much easier for the people who are familiar with the conventional programming.
Okay. Thank you.
Thank you.
Any other questions?
Can I just add some comments?
Use the mic.
Yeah. About graph pattern matching, we also tried graph simulation, which is a inductive definition and also recursive. Yeah, right. So that one is very easy. Using this one, we just plug in sequential algorithms and do it. To your second question, well, some people find it more comfortable to deal with the conventional programming, right? So like Jingbo and Wen Yuan did POC at online payment bank, and those guys find it so hard to use a vertex-centric model. They said, okay, how could I add a loop to range over all the vertices, and they find it useful. I mean, like easier, much easier to use this one. That's what Jingbo see.